Hello, and welcome to Pale Blue Pod, the astronomy podcast for people who are overwhelmed by the universe but want to be its friend.
I'm Connie, your curious friend and co-host.
Yeah, you are. My friend, too.
Yes.
I'm Dr. Moiya McTier. I'm an astrophysicist and a folklorist and a friend to the universe. Connie, do you feel seen by the universe lately?
Great question. I think so. I mentioned either last time or the week before that I hadn't gotten any plant time. I've gotten some plant time in. I've tried to be out, get a little bit of sun to really feel seen by the universe in the most literal sense. And yeah, I'm feeling like nothing super, super exciting's going on, but nothing super, super bad's going on to me, personally at this time in my
love that for you.
Life journey. And so I feel content and trying to hold on to that. Like, okay, don't go away. Don't go away.
Mm-hmm.
The anxiety wants to ruin the contentness, but I'm trying to feel close to the universe.
Mm-hmm. Stay grounded.
Yeah.
Or clouded, whatever works for you.
Yeah.
Hopefully the universe will see that.
Yeah, there's a little haze, but I think it's clearing. There are clear patches.
Lovely.
My emotional weather forecast. How are you feeling, bestie? Are you feeling seen by the universe?
I feel like... Okay, so I have this thing. I have this thing called pronoia, where I do really believe like the universe is looking out for me and it's working behind the scenes to make things go in my favor. And sometimes that means the universe sends you things that you don't want or think you need, but ultimately you do. And I think that is what the universe is giving me lately. I feel like it is seeing me and saying, you need this. You don't want this, but this is good for you, so take it.
Gotcha.
Mm-hmm. The universe is forcing me to like make some decisions and choose between things. I hate making decisions.
Yeah.
I'm a bisexual astrophysicist folklorist. I hate making decisions.
Sciences, humanities, why choose?
And I love why choose. I never want to choose.
Maybe you're just starting your own why choose. This is how they begin sometimes. Anyway, today we're talking about light, a specific region of the light spectrum, of the electromagnetic spectrum. And I asked Connie which region she wanted to start with, and you chose UV. Why I did.
UV?
Because I think the two that I am... See, I feel like I'm about to say something wrong anyway, because you told me what the spectrum was, and then I forgot already. But microwave is part of the spectrum, yes?
Yes.
So microwave and UV, daily life, like in those specific words, like microwaves and just like wear sunscreen or on your app, on your weather app or whatever. So it's something that I like kind of know what it is and I see it a lot, and so I'd like to understand it more. And then we'll just go on down the list of all of them, because it's true for all of them, but some of them I think I've obviously you come into contact with more frequently in the explicitness of them being as part of this spectrum, if that makes sense.
Yes.
I think they get removed from being part of a larger spectrum, which is why I also was like, oh yeah, there is a spectrum, and microwave and UV and all these other ones are on the same one. Like that's the thing that I also kind of get disconnected from in everyday life.
Yeah.
But UV rays, like wear that sunscreen, girl. And then I'm like, okay, so explain that. Like, how does that? What is the science behind that? And what else? This is part of my questions, because that was one of my questions. And the other
Can we do one question at a time?
Oh, you're going to answer them individually. Okay, yes, sure. Yes.
I'm not just going to make you ask them and then not answer them.
Oh, well, I thought they would go, as in the course of the episode, you'd tell me the answers.
In the course of the episode. Yeah. But we can talk about it up front.
We can do. Okay, great.
Okay, so what's the first question?
Oh, basically how sunscreen works.
How sunscreen? Okay, yeah, so I wasn't going to talk about that later.
Because I wanted to know, before I know how sunscreen blocks it, I wanted to know how it worked. So I wasn't sure if that was like, we'll say how it worked and then, about like protecting yourself from it. So I wasn't sure what the order was, yeah.
Oh, from what I know about how sunscreen works, there are a few different types. You can have a physical barrier where you have something like zinc or a thick paste that acts as a physical barrier that the light waves can't get through. You can also have a chemical reaction that either absorbs the UV light or reflects and repels the UV light so that it doesn't get absorbed into your skin.
So what else produces UV light besides the sun, or is it just the sun? Because that I'm not sure about.
Yeah, the sun definitely produces most of the UV light that we encounter in our daily lives, but any star is going to produce UV light, and I'll talk more about other sources later on.
Okay, great. Yeah, that's what I got for you.
Okay, then we'll dive into what I prepared. I thought it'd be helpful to start with like a primer on the electromagnetic spectrum.
Yes,
and
please.
How we discovered it. Great, awesome. Okay, so the electromagnetic spectrum is all of the wavelengths of light that we could possibly see. They can be as tiny as, a trillionth of a meter, even smaller. They can be as big as 100 meters across. The really, really tiny ones are called gamma rays. So that's kind of like an open-ended limit. Anything with a wavelength smaller than, I don't know, some tiny number like a nanometer, that's going to be a gamma ray.
Okay.
Anything bigger than like 10 centimeters, I think, is a radio wave. So 10 centimeters all the way up to 100 meters. That's going to be radio waves. We obviously knew about, the optical part of the spectrum that sits right in the middle. That's the part we can see. We've known that for a long time. People from like Aristotle to Newton had their ideas about how color worked. But Isaac Newton in 1665 was the first to scientifically show how different colors worked by taking a prism, a piece of glass, holding it up to sunlight and letting the light that passes through be split up into different colors.
Right.
So he saw that for the first time, saw white light being split up into different colors. But we knew that there were color, like we had rainbows.
Yeah.
We saw
reflections
the light
in water.
refracted.
Yeah, on water, right?
Yes. Although refractions, not reflections.
Right. Yes.
But we can also see the things that happen because of refraction, like rainbows reflected in water. So yes.
Right.
But he didn't do anything else with it. That was part of his really busy year. Newton at the same time was, studying, like inventing calculus and studying gravity. So it's okay. He didn't need to go all the way with colors. Yeah. It took until 1800, this is another 135 years, for us to do more with the spectrum of light. So in 1800, William Herschel did what Isaac Newton did, and he split the light up into its different colors. And then he put a thermometer in each of the colored bands. He was really interested in the study of heat and temperature. There's actually an infrared telescope named after him, the Herschel telescope. And he wanted to see if blue light was colder or hotter than red light, or if they were the same. And so he put a thermometer in each of the different colors, and then he noticed that the red light is hotter.
Okay, so how big was this? Like, how big was the glass? Like, do we know how big the glass was, and then how big the thermometer was to just be able to like I'm imagining like seeing a diamond or something that shows like that rainbow, or like the Pink Floyd, like visual of the album cover. And so just like, I'm just imagining just like one of those old mercury thermometers just being like held in the air where light is. So help me?
No, he shone the light through a prism onto a table, and then you could see the rainbow on the table, and he put regular size thermometers in those rays of light on the table.
So like if you have, a prism in your window and the sun's coming through and it's showing you a rainbow on your table, and you just put out a thermometer and you could measure each one, and would it be statistically different on like a home thermometer, or is it like,
I mean, he did this in the 1800s.
You're right. Yeah. Like, Huh.
Yeah, this was with like an old school mercury thermometer
Yeah.
and you need one for each wavelength, one for each color, so you can compare them at the same time. But yeah, if you have a big enough prism, you can create a big enough rainbow to do that, no problem.
Yeah. I never thought about it being that, like, the temperature of the light if the sun's on your skin, it kind of all feels the same. But when it's through the prism, you can then like literally split it like temperature wise. And that's the thing.
I think people don't understand that a prism doesn't just split it up so that we can see the colors. It is literally splitting up the photons of light, because the way a prism works is that as light comes in through one side, it gets refracted, meaning it gets bent, and the different wavelengths of light will travel at different speeds and at different angles through this medium, because the speed of light is only constant in a vacuum. If it's traveling through any other substance, it changes. So the blue light is going to get, diverted at a different angle and at a different speed than the red light. So they are literally, those photons are following different paths.
Wow.
Yeah.
And it's that same path, the Roy G. Biv kind of spectrum. Like, it's always the same.
It's always going to be in that order, because the angle at which the light gets bent through the prism depends on the wavelength of light. And the red wavelengths get bent less than the blue wavelengths. That's why the sky is blue, because blue light gets scattered through our atmosphere really easily. And so then the red is at the top of the rainbow because its angle has been bent less, and the blue is at the bottom of the rainbow because it's been bent a lot.
Okay.
Yeah. So Herschel did that with the thermometers, and he went an extra step beyond, and he put a thermometer outside of the red light because he noticed that red was hotter than blue. So, maybe the temperature just keeps increasing. And he found that if you put the thermometer outside of where the light looks to be shining, you do get a higher temperature than with the red light. So he called them heat rays. And for a long time, we were calling them heat rays. Now we call them infrared rays, infrared light.
Oh, okay. Infrared.
So that's 1800.
Okay.
The next year, in 1801, now people are like, oh, there are different wavelengths of light. There are things we can't see. And there's a balloon. There's like a burst of advancement in the field of optics. So in 1801, a chemist named Johann Ritter in Germany, I looked it up. It seems to be no relation to John Ritter, the actor.
I was wondering.
I knew you would.
I was wondering a little bit, because it was like Johann Ritter, and just this John. Especially if you look at it too fast on the paper, it's just like, it's John Ritter.
John Ritter. John Ritter discovered UV rays. Let's start the rumor. John Ritter's great uncle, Johann Ritter, discovered UV rays.
Who knows? Only Henry Louis Gates could prove us wrong.
I had an image in my head of who John Ritter was, and it's not who I thought it was when I actually Googled him. And who it ended up being, when I saw the picture, I was like, oh, that's the guy who plays Buffy's robotic stepdad in that one episode in season 2. And I don't know anything else that he's been in.
I mean, he was famous before, what was it called? 8 Rules for My Daughter. But like, he was iconically on an ABC sitcom for like several years before dying on the show. So like, they had to deal with that on the show. Yeah.
Oh,
I didn't
he's dead?
ever watch it. Yeah.
Oh, R.I.P. I didn't know. Sorry. I'm sorry, John.
Yeah. Yeah, his son is an actor now.
Is his son who I'm thinking of? We're having live lessons learned on the mic.
I love how you looked up, like you took the time to look up if John Ritter was related to the chemist, but didn't find out about anybody else he was related to, nor whether or not he was still with us. We're just doing it for the science, okay, guys?
Yes! I was thinking of the hotter young son.
Yeah, that's his son. Yeah.
Okay, cool. Who is not dead.
No.
But is the great nephew of Johann Ritter.
Here first, and maybe only here.
Okay, let's get back to science. That was a fun detour. So Johann Ritter decides to do basically the opposite of what William Herschel has done and examined things on the bluer end of the electromagnetic spectrum. Except instead of thermometers, he's using like photography paper.
Ooh.
And he places a little slip of paper that's soaked with silver chloride in each of the beams of light, and then one outside of the violet part of the spectrum. And what he notices is that there's this invisible light beyond the violet part of the spectrum that darkens the photo paper faster. Because they already knew that this photo paper would darken faster in blue light than in red light, so he wanted to take it to the extreme. And he called them deoxidizing rays. And then other people started calling them chemical rays or chem rays before they were eventually called ultraviolet.
Right. Okay. Yeah, because I in high school I took a photography class and we did old school, so we went into the dark room and like used, the different chemicals and light to make the photo paper darken. And I'm sure they did a lesson on how that works, and I'm sure I immediately forgot how it did. But in those rooms it's always like a red light for anyone. I mean, maybe you've seen it on TV or a movie or something. But, it's always a very dark.
You do the red light so that it doesn't process the photos, but you can still see them.
Yeah, so that you can still see in the room. And then you put the photo paper in like a chemical solution. Again, I've forgotten, but I think different ones can, produce different effects. So we were playing around with that. And then the stuff starts to happen and the picture starts to form. And it's very cool. And then you got to hang them in there and wait for them to dry in that red light still. It's very interesting.
Oh, so they stay in the red light. You don't put on some UV light after you leave? Is it because you don't want them to oxidize?
I honestly can't remember. Yeah. I honestly can't remember because maybe the paper is doing the solution is doing some work there so that, but you don't want it to oxidize.
Yes.
Yeah, I think it's just the red light. But it's been a while, so I'd have to look back into it.
Okay. Interesting. Yeah, I thought you'd get excited by the photography connection.
Yes.
So let's talk about some characteristics of UV light now that we know it was, this actor dynasty's ancestor who discovered it.
Totally.
So UV light has a wavelength range of between 10 and 400 nanometers. Okay. 1 nanometer is 1/1000th of a meter. So to give you some comparisons, the wavelength of ultraviolet light is about the same size as either ultrafine dust particles, the type that you need like super advanced HEPA filters to get rid of, or most viruses.
Wow.
It is split up into different sections of ultraviolet light or different types of UV light, A, B, and C. We are so creative.
At least the colors have names when you get to the different way, you get back to optical or, and then at least we have color names. And it's like, okay, that's really small. Let's just ABC, just keep it simple.
ABC. Yeah. We don't need to fuss anymore. So A type light for UV is the longest, least harmful type of ultraviolet radiation. This is what black lights are. You can shine those. They're not going to affect your genetics or anything.
Right.
They're fine. This type of ultraviolet light is not absorbed by the ozone layer. It just comes right through. So this is the type of UV light that we see around us. It's also called soft UV light, especially by astronomers.
And when you say we can see it, what do you mean by that?
I mean all of the UV light that actually reaches the surface of the Earth coming from the sun is UVA light.
Okay.
So if you were to put on UV goggles, you would be seeing only UVA light.
Gotcha. Okay.
Yeah.
So not with the naked eye, but with,
Correct.
those goggles. Okay.
The other types of UV light do get absorbed by the atmosphere. So that's the only type of UV light that our atmosphere lets through. So type B, we're getting a little bit more dangerous here. The wavelengths are shorter, so the energy is higher. This is between 280 and 315 nanometers. It's a really small window. But this is the first type of UV radiation that's going to give you skin cancer. This is going to affect your eyes and give you cataracts. This is the type that can be dangerous for crops. And luckily, our atmosphere, specifically the ozone layer, absorbs about 90% of this UVB radiation.
Okay. And that is good. I mean, obviously it's good for us, but I'm saying it's good for the ozone layer. That's fine for the ozone layer, or is
it hurting the ozone layer to absorb all of that?
Yeah.
Great question. So let's talk about the ozone layer. It is a part of our atmosphere about 9 miles thick. So it extends from about 9 miles above the surface to 18 miles above the surface of Earth. And ozone is 3 oxygen molecules together. So when we say oxygen, like the type of oxygen we breathe, scientists call that molecular oxygen. It is 2 oxygen atoms bound together. Ozone is 3 oxygen atoms bound together. I'm sorry if I said molecules or particles before, but it happens when strong radiation, like ultraviolet radiation from the sun, ionizes or splits apart molecules in our atmosphere. So the ultraviolet light can actually split apart a molecular oxygen particle. And so then you have 2 single oxygen atoms. And those 2 atoms can then bond onto molecular oxygen. So you get 3 oxygens together. And that's how we produce ozone. So we need the ultraviolet rays and the X-rays to make ozone in the first place. Yeah.
Okay.
So we need ultraviolet radiation and other forms of radiation to produce the ozone, but it can also be destroyed fairly easily, especially if you have chlorine or bromine. Those are 2 elements that can just rapidly, through chemical processes, destroy ozone. A single chlorine atom can destroy 100,000 ozone molecules before it is depleted. So when people were talking about the ozone layer's hole and the depletion of the ozone layer, it was because we were emitting a bunch of chlorine and bromine-based pollutants. So chlorofluorocarbons are the ones that people really talk about. And then bromides. Those are bad. They will actually rip apart this protective layer in our atmosphere. And that's what they were doing in the 60s, 70s, and 80s. And now it's getting better because we said you can't do that anymore.
And it was like refrigerator stuff like that, like appliances, like refrigerators and hair dryers
and hairspray and pesticides and things like that.
Because that was a big, of the cultural part of that conversation. So that's, and then we stopped doing those things because the scientists were like, hey, stop doing the thing. And people were like, man, we should really tell people to stop doing this. And then people stopped doing it. Look at that.
It's amazing when people listen to scientists' recommendations, and then we can actually reverse some of the things that our stupidity has led to.
Yeah, because it was a hole, and now it's like, it's less of a hole.
Yeah, but we do still have an atmosphere, and that is great because the atmosphere will absorb 90% of the UVB radiation and basically all of the UVC radiation. This is the real dangerous shit. The UVC radiation is from 100 to 280 nanometers. This is what ionizes molecules. This is what kills germs. So when you use like a UV light to kill germs, I have this on my toothbrush holder. Yeah, that like strong blue light. That light, that radiation is strong enough, it produces enough energy and therefore enough heat to actually kill germs and some bacteria. And it is called hard UV by astronomers and luckily also definitely absorbed by the ozone layer.
And we're giving it to consumers?
Yeah, we give it to consumers. We say don't look at it, and people are dumb, so they do. And read instructions. Hey friends, it's me. Connie is going over every inch of the office with the blacklight and finding all of the affirmations I've written for the bees and the birds and the other insects who fly in here and can see UV light. So I figured I'd take this opportunity to share some messages with you. The first message is a huge thank you to all of my patrons who support the show every month. We are an independent podcast, so it'd be really hard to make Pale Blue Pod without your support. And I definitely want to give a special shout out to my sun-like stars, Scott Reynolds, Tom T, Nicole Bartlett, Ashley Shambo, Mark Mahoney, and Bruce Sedloff. You're all golden, and I want to thank you from the bottom of my heart for all of your support over the years. Some of you have been with Pale Blue Pod for a very long time, so thank you. If you want to support this indie podcast, hear your name on the show, make it onto the patron star chart, and get research notes for most episodes, you can do that for $5 a month at patreon.com/palebluepod. You could also make a one-time donation and become a supernova in the Pale Blue Pod sky. That's at the PayPal link in the episode description. And of course, if you can't support the show financially right now, we understand and we love you still because you are space. The best way to help Pale Blue Pod grow is actually to get more people listening to it. So if you could please send the link to this episode to someone in your life who is interested in light or who tans a lot or who has gotten really into those light therapy masks lately, then you're teaching them about the universe, you're helping them get closer to it, and you're helping Pale Blue Pod grow. So thank you all around. My next message is a podcast recommendation. It's another show in the Multitude Network, and it's one of my personal favorite podcasts. Spirits is a history and comedy podcast focused on everything folklore, mythology, and the occult, told through the lens of feminism, queerness, and modern adulthood. Every week, mythology buff Julia and her childhood best friend Amanda get together to learn about a different story from mythology and folklore over drinks. They talk about everything from the mythological origins of major franchises like Lord of the Rings and Pokemon to modern urban legends that listeners send in and they read on mic to a roundup of like werewolf stories from around the world. I just listened to their Will-O-Wisp episode. They put it out last month. I'm a little behind. And it was so fun to hear all of the stories from around the world of this one single phenomenon that I grew up hearing about. And so check out Spirits. You can listen to any of their more than 450 episodes that they've released. They've been doing this for 9 years, which is really impressive. So dive in at spiritspodcast.com or search for Spirits wherever you download your podcasts. Okay, Connie has looked over the whole room now. My favorite is the message by the door that reminds our UV-sighted visitors that they are more than just their wings. And I'll ask Connie what her favorite is later, but first let's get back to this episode. So those are the different types of camps of UV radiation, I shall say. And then within those, there is like an interesting type of radiation, like very specific wavelengths of light that astronomers pay attention to because they tell us what hydrogen is doing. Hydrogen is the most abundant element in the universe. About 75% of the whole universe is hydrogen. And if we can use hydrogen as a tracer in different environments, like in different stellar systems or in different galaxies, then that gives us a sense of where the material is.
Okay.
So there is this very specific type of radiation called Lyman radiation, and it's a series of different wavelengths that we pay attention to. So the Lyman series has Lyman alpha radiation, Lyman beta radiation, Lyman gamma, and it goes on like that. They're all named after the person who discovered them. His name is Theodore Lyman, and he did this in the early 1900s. I think he discovered the first one in like 1904 or 1906. And like the Lyman alpha wavelength corresponds to a photon that is produced through a very specific process. So if you have a hydrogen atom, it has the proton and the neutron in the nucleus in the center, and then there's the electron around it. And maybe there are more electrons if it's not a neutral atom, but these electrons live in and move between shells. You've heard of the electron energy shells?
I think so, yeah. I'm picturing my textbook, a science textbook with the picture of the like you just mimed it out. I was trying to figure out what the word would be for our listeners.
So you're picturing the atomic model where there's the neutron and proton in the nucleus in the center, and then there is a very neatly defined set of concentric circles where the electrons move.
Correct.
Yes.
Yeah.
That is a good basic proxy for what's happening. But in reality, the electrons are in these like quantum clouds of positions around the nucleus of the atom. But for now, all we need to think about is that sometimes electrons can be in like higher energy states and sometimes they can be in lower energy states.
Okay.
An electron will bump up to a higher energy state if it absorbs energy, if that particle absorbs energy from a photon.
Okay.
If an electron jumps down to a lower energy state, that particle will emit a photon. It will send out a photon. And the energy of that photon is going to exactly equal the difference in energy between those two levels that the electron traveled between.
Sure.
So when we see a photon and we measure its wavelength, which also tells us how much energy that photon has, we can then know how much energy did the electron in the particle that produced that photon lose.
Right.
Okay.
Yeah.
Okay. So the electron can jump from like the second energy shell down to the first. And that the photon that's emitted in that process, that gives us the Lyman alpha line. And then if the electron is jumping from level 3 to level 1, that's Lyman beta. Level 4 to level 1 is Lyman gamma, and so on down the line.
Okay. And you can tell how much it lost, or I guess gains. Is it only about the loss of a photon?
It produces. Yes, it produces and emits a photon, yeah. It's not like the photon is in there and then it's getting kicked out.
Right. Okay. But then you were saying that the Lyman scale is about that difference, right? But it's only if it loses, if it emits a photon, or is it also when it gains a photon to jump up a level?
Oh, now you're talking about the difference between emission and absorption.
You got really excited. Your face is so excited that I asked you that.
I did get really excited. Because I didn't expect the conversation to go there. Yes. So it's about all of the nature, all of the behavior of photons. Photons can be absorbed by a particle. When that happens, the particle gains energy. But we don't see that. What we see then is the absence of a particle. So when we look at a planet's atmosphere, for example, and we're trying to get a spectrum of that planet's atmosphere, we will see dark spots in the spectrum because those particles that correspond to those wavelengths of light have been absorbed by the planet's atmosphere. So we'll see those as dark spots. On the other side, we will see emission lines where you can see that a planetary atmosphere is producing some type of molecule, and we would see those as bright spikes in the spectrum when we analyze it.
Okay.
I'm so glad you asked that.
And that's all a Lyman alpha, Lyman beta, or is it?
So the Lyman series is specifically for these particular transitions of electrons in hydrogen molecules. So we look for those everywhere because they have distinct signatures and they're relatively easy to find. Right. The Lyman alpha emission is at about 121 nanometers, so that's firmly in the UV. All of the other Lyman lines are also in the UV going into the X-ray because as you go up in the Lyman series, so like up to beta, gamma, delta, the lines get closer together and their wavelengths get shorter, so their energy is increasing, which makes sense, right? Because the photon that is produced when the electron goes from shell 7 to shell 1 should be much higher energy than the photon produced when the electron goes from 3 to 1.
Okay.
Yeah. Bestie, you just heard about superfine atomic emission and absorption lines, which is something I didn't start understanding until I was doing research in grad school. How do you feel?
I feel like I'm picturing things that are very simplistic, and I hope they're close enough. That's how I feel. I'm trying, it helps to visualize, And then that's why, when I was like, okay, I remember that from my textbook. And when you added that, it's like more like clouds. I'm like, okay, cool. I changed them immediately. I'm like, okay, the electrons are little clouds. I can see it. And then so I'm trying to just visualize it and hope that it's close enough and helps me understand.
Gosh. I'm finally going to answer your second question, which is what else produces UV rays? And the short answer is it's the hot stuff. The hottest gases actually behave in a way that's different from gas. They have behavior that matches the fourth phase of matter called plasma. Because as you've heard of plasma. Okay, good.
Yeah.
Plasma is essentially just a soup of charged particles, and it happens in these really hot environments because all of that energy makes it difficult for the electrons to stay on their molecules. So they'll move away, and then they are charged, and then the molecule that they just left is now positively charged. So you have this soup of charged particles. And specifically for plasmas that are above 1 million degrees Kelvin, which is like several million degrees Fahrenheit, that's going to make ultraviolet light. So you see this with new stars that are formed. You see this in galaxies that have a lot of star formation. And you also kind of see this at the very end stages of some stars when they start to heat up right before they're done fusing. And so you really see UV light coming from very young and very old things, as long as they're hot enough.
So do we see plasma? Is looking at a star kind of seeing plasma? Do we see it on the optical?
Stars are plasma.
Okay.
They are swirling balls of plasma, and we can see. It's not that plasma only emits in the ultraviolet. It's just that it very strongly emits in the ultraviolet, but we can still see it in the optical. Yeah. So our sun produces a lot of UV rays.
Yeah.
But our sun actually peaks in the optical part of the electromagnetic spectrum. That is why we see in this part.
Yeah.
Because we evolved to be in tune with our own sun. But hotter stars like A types and B types, they will peak more in the ultraviolet. This is because we typically think of stars as black body emitters. Not the best name thing in astronomy.
No,
I'll say that. I'll say that.
Not for the black astronomers, but yeah.
No. So black body radiation is when you have an object, a theoretical object that absorbs all energy that shines down on it and then re-emits it as heat. And it is in perfect thermal equilibrium with its system. So a black body curve essentially represents all of the energy of an object in terms of its temperature. And we have a relationship between the temperature of an object and the wavelength of light that it's going to shine most brightly in. This is called Wien's displacement law. It's German or Austrian or something, so it's Wien with a W.
Oh, okay.
And Wien's displacement law says that as you go up in temperature, your peak wavelength goes down. But that's also the same as saying that as you go up in temperature, your peak energy goes up. So I think it's more intuitive if you say it that way. Yeah, so like a very hot O-type star is going to have a black body curve that peaks at a lower wavelength but higher energy than a very cool, dim M-type star.
Okay.
And that's where we get UV, the UV rays. Out in space. We can also produce them here on Earth. Like you can generate them by passing electric currents through specific materials or But we can also just use them. We can use UV rays in very, very cool scenarios. So I talked about killing bacteria. Apparently we discovered that we could do that back in 1878.
Is this like about just like using the sun to like bleach stuff? Like, is that part of this? I feel like I feel like there's a thing where it's like, oh, if you in your bedroom, for instance, like keep your, get some light on in your room to like help clear. And I don't know if that's just like old wives' tale kind of thing.
Do people say that?
I feel like I heard it once. Not like a saying, but maybe it stuck with me because I was like, yeah, I should make sure there's light in my room. It helps. Not just for me, but just like for the environment of your room.
Yeah. I can see that becoming a piece of folklore that is passed because we know sunlight is good for us. I don't think, especially because a lot of the windows that are used these days block even more ultraviolet light than what already gets through our atmosphere. But it is good to get sunlight in your room, bestie. So keep doing that.
Yeah, I will.
Hi, this is fact checker Moiya coming in to say that I did look into it, and there seems to be some scientific evidence. I even found an NPR article. It's in the research notes for the episode for patrons. There seems to be some evidence that prolonged exposure, and I'm talking at least an hour, to sunlight can reduce dust mites and bacteria levels. So I guess throw open those curtains, folks, and maybe don't make your bed. Leave the sheets open so the sunlight can hit them. I will. But yeah, I think back in 1878, they were using other methods to produce these ultraviolet rays. Sometimes dermatologists will say that if you have bad acne, you know, like a good, like one sunburn can like really help you.
Whoa.
That is from the UV rays from the sun killing the bacteria that would cause acne. But now we can do that in fancier and more regulated ways with light therapy.
Oh, is that what's happening? Because I've seen a very strong increase in use of these like light masks. And, you know, it's kind of like, are those two different things?
No, we're talking about that.
Okay. Because like obviously it's like in the beauty circle, and so I didn't really understand why. I was like, okay, I just didn't look into it. So is that what it's meant to be doing? Is to like kill the acne bacteria?
So in this case, when I looked up how light therapy works with the masks and everything, it inhibits the DNA generation in your face, so that you can't produce more skin cells to have acne or psoriasis or eczema or something like that. So the way that this light therapy literally works is by destroying your body's ability to generate DNA in that specific location.
Oh, in that
specific location. Although, like, I don't know how much it travels, you know?
Right. Because that seems like it could be bad with overuse.
Yeah.
Okay.
So that is how it works.
I mean, I can't judge. I do gel nail polish, which I know we'll
get to. Because the gel. Yes, the curing. Now we're talking about most of the uses that I found for UV light here on Earth were beauty related. Like there's you know, like the cleanliness aspect to it with killing bacteria, so sterilization and sanitization. But it's a lot of beauty stuff. So
that's interesting.
Yeah. The curing process. This is, you see this with nails. You see this with printer ink too. The way it works, it's a photochemical process. So the UV light will initiate a chemical reaction that makes a special binder molecule. A lot of research, I'm sure, went into finding that specific binder molecule. But when it's exposed to this type of light, all of the binder molecules around each other will attach to each other and make the material solid. So this is a way that you can have a liquid that then is turned into a solid by light. And it is the higher energy radiation that is able to do this. So if you get regular manicures where they have to cure it using UV light, you are exposing your body to the same type of light that actually, changes your DNA. And that is why people are talking about it being dangerous. Yeah. Do you do that? You don't do. I've never seen you do that.
I do.
You do that, bestie?
I do.
Oh, okay. I've only ever seen you with the is it press-ons? Is that what they're called?
Yeah, I've used a bunch of different types. I've done my nails with regular nail polish. I'll do it with gel. And so I have a UV light to cure my nails. And I've started putting on sunscreen. I don't always remember, but I put on sunscreen before. It's like here's my hack for any of the melanated girlies. If you've gotten a sunscreen that you don't like because it leaves a white cast, but maybe it was expensive or whatever, if you want to keep it, use it and you do your nails with gel polish, obviously, maybe a subset of people, but maybe put it on your hands because you don't have to, like, it's a way to use it without like getting rid of it. Cause I had some that even on my fair skin was like leaving a too much of a white cast that was going to be like, absolutely not. And I just forgot to return it, never gave it to anybody. Yeah. Like I don't need to be reflecting light in the sun, you know? But more light anyway. And so I was like, I don't know what to do with this. And then as I was, probably some TikTok I saw that was like, oh, you could use sunscreen, or it just made me think about like, yeah, the sunscreen is to protect you from UV rays, and this is a UV light. So ipso facto, like it couldn't hurt. It didn't seem like it could hurt, even though I'd only seen like maybe one reference to it, but 1 + 1 = 2 in this instance. And so I want to do it more consistently. I keep the sunscreen with my nail stuff, and yeah, it's just like helpful because it's just like you can see that it's on, and and I do my nails, like you have to make sure your nails are clear of like product and stuff, and so I have to do a better job of clearing it off because then the stuff doesn't really bond to my nails as like it should, because of all the oils and stuff.
And because you're inhibiting the UV light.
I'm inhibiting the UV light with the stuff. So that's one way, I guess, to maybe at least lessen the effect. But also now I'm thinking about like the people who have these light therapies on their face, and I'm like, but you can't. I guess sometimes they're red. Like, is it bad to look at it? Because it's bad to look at, like, they tell you it's bad to look at the nail polish one. So like, I'm sure I've accidentally, like, it reflects.
It is a different type. So I don't know exactly what the wavelengths that they use are, but if light therapy is like UVA or UVB radiation, then the curing is UVB or UVC.
Gotcha.
Like the curing is just
the
more
strength.
Extreme.
Yeah. That makes sense.
So outside of Earth uses for UV light, we also obviously want to study the whole universe in it. I think the most exciting thing that we've discovered, thanks to UV light, that we would have had trouble seeing in other wavelengths, is that our solar system is in a giant local bubble. Have you heard of this?
No. I don't think so.
Our solar system is in an underdense region of space about 1,000 light years across. And there's just like way less material here than there is in other parts of the galaxy, even at the same distance from the center. So what we think happened is that about 14 million years ago, up to 1,000 supernovae went off in this one location.
Just a big fireworks celebration of something.
Yes.
Okay.
Yes. And that's not unheard of. We know that stars form in groups. We know that stars form in clusters of thousands sometimes. And most of those stars are going to be low mass, so not massive enough to have a supernova go off. But some of them will be quite massive. So in this area, about 14 million years ago, all of these supernovae went off. They produced these super powerful shock waves, pressure waves that literally pushed the material out from this central location for 1,000 light years. And it has stayed in that one location while other parts of the galaxy, through their conserved momentum, continue to spin. So about 5 million years ago, our solar system entered the bubble. And we know that because we have found radioactive elements on Earth's surface that correspond to those type of supernovae that would have gone off 14 million years ago. So we know that we passed through a cloud like that, and we can kind of like reverse engineer the trajectory of the solar system to figure out when and where it happened. And so about 5 million years ago, we can tell we passed through the shell of this bubble, picked up some of the radioactive material from the supernova explosions, and we're going to spend 10 to 20 million years from now passing through this bubble as it continues to slowly dissipate away.
The bubble is dissipating?
Yeah, the bubble's dissipating. So by the time we actually travel 1,000 light years, which is going to take us like 10 to 20 million more years, we probably won't pass through the other side of the bubble. Like it will have fizzled away by then.
Because things have filled the spaces?
because that material that was carried away in the initial shockwave is still moving and will continue to be carried away.
Yeah. So, okay. So it's just like spreading out.
Dissipating, yes.
Yeah. Just had to... Okay.
Yeah. Isn't that cool?
Yeah. It makes my brain hurt, but it's cool. Because it makes my brain hurt. Because I'm just imagining our little solar system just... And then it's like, okay, we're on this, like, slide, and but the slide is, like, breaking apart. I was just, again, I try to picture it so I can understand it. And
what's the slide in your metaphor?
The shell of the bubble.
We're not traveling along the shell.
Okay. I thought for a while we might.
We traveled through the shell.
Okay. I gotcha. Okay.
Like we're going through the center of the egg. We're not traveling along the shell.
Oh, okay. Because I thought it was like, oh, we hit the shell and then we like glided along because it was breaking apart and we're still going. So that's where I was like, oh.
No, the shell is stationary.
Okay, yeah.
The center of it is stationary. But other things in the galaxy, through their momentum, are being carried through and out of the shell slowly. Because I think a lot of people have this impression that the stars and other, if they have an impression of stars orbiting around the galaxy, they imagine that everything is swirling together, and that is not the case. Individual objects are moving, and they tend to move in the same direction and at similar speeds, but they are all moving as their own thing.
Right. So that's what was coming to mind. But I guess I was still seeing our galaxy as its own whole, because it is its own, like, succinct, like, set of space, and then where everything's moving inside of it in turmoil. But the whole thing is, I imagined it just, like, coasting off of this
The galaxy
space.
is also moving.
Right, yeah, I imagine the whole thing coasting off of...
I'm agreeing with you.
Yeah.
Yes, the whole galaxy as a combined unit is moving together. Yes. Yeah. Because we talked about the traffic jams and the spiral arms.
Yeah, so I was like, oh, this one little car with its wacky children, inside, a clown car of planets.
I like the solar system as a clown car. Yeah, let's keep going. Okay, so what happened here? I'll finish the metaphor for you. Our solar system is in the clown car. The clown car passed through a ghost town.
Yes, okay. Great.
Yes. The clown car is right now passing through the ghost town. When we passed through the shell, what we did was pass the city limits. And we were in the car, and Earth saw the sign and was like, oh, well, we're here now. And maybe we shouldn't get out of the car after dark. And Earth saying that in the metaphor is the same as Earth collecting those radioactive materials that then let us know we passed into the shell.
Right, yeah.
Yes.
Gotcha. Like the waft of an old something was in the car as you continued to go along. It's like, wow, that town smelled this particular way.
Yes, exactly. I feel like you have a nice image of a town in your head, and
it's just
have
empty.
A sundown town in my head.
Oh, it's just empty, like an old Western town in a set. But
that's fun.
Kind of like a set on like a TV show. Yeah. There's a particular, I feel like there's an episode of a TV show that's like in my mind where there was like an empty like Western town set, but I can't remember which show it was, like Charmed or Psych or something.
Oh my God, it's Charmed. I know that episode.
Like that.
It's the episode where Prue and Cole go back in time, and I know where they get trapped in this like old Western town. Yeah.
Yes. Yeah. There was a lot of 90s like old Western episodes.
The amount of space knowledge that I could have in my brain if I just didn't know.
No, okay.
This random episode of Charmed.
Moiya, I think you're fine. You have so much space knowledge already in your head. You're good. You're good, my friend. Please, trust me. It's like, I wish I could have more. And I'm like, I'm still just trying to follow along with the Earth metaphor, okay?
Okay, you're right.
Anyway.
So Earth is traveling through an old Western town. Our entire solar system in the solar system clown car is traveling through. And I don't know if our other siblings in the clown car noticed this smell of old gunpowder, but we here, the Earth sibling, we did. We know.
Absolutely. We know.
And we know that thanks to telescopes and other instruments that are dedicated to studying ultraviolet rays. There are, unfortunately, fewer telescopes that are solely dedicated to UV than other regions of the electromagnetic spectrum, they usually get lumped in with optical or X-ray observatories.
Okay. That makes sense, I guess.
Yeah. But there are still a few that are mainly UV. One is called the Colorado Ultraviolet Transit Experiment, or CUTE.
Love that. I love that,
I know.
obviously.
I thought you would. They are not trying to find new planets. Instead, they are targeting known planets to study their atmospheres as they transit in front of their stars, because it also has a spectrographic instrument. Then we have the Lunar-Based Ultraviolet Telescope. It is based on the moon. That is an appropriate name. This was launched on China's Chang'e 3 spacecraft. So they went to the moon and they soft landed on the moon. Chang'e 3 was the first mission to soft land on the moon since the Soviets in the 70s or 80s.
Wow.
Big deal. It did that in 2013. Yeah. And the LUT is meant to study galaxies and bright stellar objects, so like supernovae or stellar remnants. It also has a camera, a UV camera, to not study things outside, but turn back and study us. So it is studying Earth's plasmasphere. Did you know we have a plasmasphere?
No.
Neither did I.
And where is that?
The plasmasphere is a part of our far exosphere, like the very last part of our atmosphere. It's kind of wrapped up in the magnetosphere of the Earth, but it is cold plasma. So I mentioned before the hot plasma that's like 1,000,000+ degrees, but plasma is just a soup of charged particles, and you don't need heat to create that soup. Around Earth, as the ultraviolet radiation from the sun ionizes particles in our upper atmosphere, you get a cloud of electrons swimming through clouds of positively charged nuclei of molecules. And so they are now positive charges and negative charges swirling around together without the high temperatures. It's a cold plasma. It's a gazpacho.
But is this gazpacho dense physically?
No, it is not.
Because now I'm thinking about plasma, and I'm like, but I don't even know if plasma is not solid, or is it? But like, if you tried to put your hand through plasma, would you? But then the heat. But then if it's cold plasma. No, it's gas. It is electrically charged gas. It could also be a fluid. Well, I don't know about liquid, but yeah, plasma is an electrically charged fluid. The cold plasma in our plasmasphere, it's not visible, definitely not in the optical part. You can only see it in the UV, and it is not very dense. Yeah, it's about as dense as our upper atmosphere is. Yeah. Huh.
Yeah.
Okay.
And then in September 2025, because space is still
just
being researched.
Just a few months ago.
We're doing things.
Thankfully.
I know. Somewhere, just a few months ago, here, NASA, launched the Carruthers Geocorona Observatory. It was named after George Carruthers, who's one of the fathers of UV astronomy, and it's going to study the top layers of Earth's atmosphere, and it's looking specifically for Lyman emission, which is why I spent so much time explaining the Lyman series before.
Also, I just love the word geocorona. That's a nice word.
It is a nice word. And I think it goes well with being named after a George. Like, I wonder if they did that on purpose.
Yeah, I do too. I feel like it must be.
But then they should have called it the Geocorona Carruthers Observatory.
They probably thought that was too alliterative. Like, almost a tongue twister.
Maybe they thought it was too cutesy.
Corona Carruthers.
Corona Carruthers. Yeah.
The Corona Carruthers.
All right, well, they had their reasons, I'm sure.
They're not us. Yeah, they're not us. I mean, you know what we would do. But
Bestie, do you have any other questions about UV rays, or have we kind of expanded your mind beyond what you thought we would do already?
Oh, my mind is expanded for sure. It's one of those things where, again, I just love a visual metaphor. It's like my brain is expanding and the wrinkles kind of like go away a little bit. And then as the processing happens, the wrinkles, it settles like a souffle.
Like a souffle. Good.
Yeah.
We're in the rising part.
Exactly.
Right now.
Mm-hmm. Exactly. So it's rising. Okay, I'm processing. I'm like, okay, cold plasma, hot plasma, the cute telescope. Like there's so many things swirling like the clown car of planets that's going through that little pocket space. So yeah. Mm-hmm. So my brain definitely feels full. Thank you, Dr. Moiya.
You're welcome. I hope it settles nicely.
It will. It will.
Great. Well, if there's no other UV stuff to cover, then listeners, remember, no matter where you are or what you look like, please wear sunscreen. Mm-hmm. Please put that sunscreen on your eyelids. They are exposed more often than you think.
Uh-huh.
And
on your scalp where possible.
Ears.
I know us thick-haired girlies, it's hard to get in there, which is helpful because then the sun doesn't. But just remember, if you like have fresh braids or like a clean part, you might want to just hit it with a spray real quick because that can, if you're going to be out in the sun all day. And if you do your gel nail polish, maybe try wearing sunscreen. It could. I feel like it could only help. Yeah.
Mm-hmm. Yeah. So wear sunscreen because you are space. And so is the UV radiation, and not all space mixes well together.
You are space, but don't become space too fast.
Oh, I like that. That's good. All right. Bye.
Pale Blue Pod is hosted by Dr. Moiya McTier and Connie Gibbs. Moiya created the show with the funny and talented Karine Caputo with help from the Multitude Productions team.
Our theme music is by Evan Johnston, our cover art by Shay McMullen, and our audio editing is handled by the superlative Misha Stanton.
Stay in touch with us and the universe by following @PaleBluePod on Instagram or check out our website, palebluepod.com.
I, Moiya, am Go Astro Mo on all socials.
And I'm @ConStar24 on Instagram.
If you want to support our show, join our community at patreon.com/palebluepod or send this episode to your family and friends group chats.
We're a member of Multitude, an independent podcast collective and production studio. If you like Pale Blue Pod, you will love the other shows that live on our website at multitude.productions.
Thanks for listening to Pale Blue Pod. We'll be back next week.